Neat. Let's just make sure that everything is fine. Still says offline so far. Okay, so now we're live. Let's just make sure the sound is okay. And it seems... all right, okay, that's good, yes. In that case, we can go back to our trusty WebAssembly binary specification, I guess. And over here, I'll open up our code. Hey, Yuya, how's it going? Hope you're doing well. So, yesterday we covered the WebAssembly abstract syntax. Well, the part of it that we care about for now. And we defined it as a PureScript data type. And so what I'd like to do today is to get started on working on encoding this representation into the binary format. So we've so far figured out how to write a specific piece of Wasm code by hand. But what I'd now like to do is to write an encoder for any kind of WebAssembly abstract syntax. So let's try that, I guess. So some of the stuff we did here we can actually keep. So the write section part, I think. These ones probably not so much. Yeah, probably not so much. And we said that reserve section size is actually kind of weird. So we're just going to say reserve section size, reserve size, and write reserved size here. And then we need to change these to say, okay, so this one can just go away. And maybe I'm going to keep them so we can reference them later. So reserve size, like so, and this one is write reserved size. And over here we're also going to reserve size, and then we're going to write the reserved size, like so. And that should compile again. All right, now we're back to compiling. Let's get started on actually encoding the WebAssembly abstract syntax. So the thing we need to do here is to change our WriteModule function, right? Right here, this is a function that just writes a hard-coded module. This is not even all that wrong in that our WriteModule function is going to look something like this, because if we recall, a module is encoded as exactly that kind of a thing, where it just where it's just like a bunch of sections in sequence in a certain order. But yeah, and what I'm going to do is I'm going to focus on encoding the sections that we care about for our little experiment, and leave the other ones for later. Okay. So let's change this to actually have a proper type. So this thing writes to a file right now, which I'd much rather not do. Ideally, I'd like this thing to return the debuffer in the end. So let's do that first. So let's just say that this returns a dynamic buffer. I do not like that one. Couldn't find a given identifier. Did we just call it debuffer? Okay, we did, yes. So just debuffer then. All right. And what this is going to do is it's going to return the buffer in the end. And really the whole thing, we might actually, now that we don't need the callback anymore, I'm almost tempted to say that this takes a syntax module and returns a debuffer and just put an unsave perform effect in front of here, because all of the effects we're performing are is mutating this buffer here, and from the outside that will not be visible. This is essentially ST, but we're doing it by hand here. So yeah, we'll what's the problem? Doesn't like this. Yes, because this is the module. Okay. And I mean, we can just do this for now and think about whether or not we want to unsave perform effects here afterwards. So I've imported syntax here under the syntax name, but I wonder if that's going to be too annoying. Maybe we want to import these things unqualified. I'm going to use S for now, and then we can decide whether or not that's a good idea after we've worked with it for a while. Oh, I'm sorry. Sorry for that one. Okay, so if we want to write a module, the header doesn't change. We no longer write a custom section here, and so the first section we want to write is the type section, so that's correct. But the type section is written into a buffer, and what we actually do here is we say module.types is what I believe. And we're going to go back and forth a bunch between these two, so maybe I should leave this one up here. Let's see if I have enough space. Encode, not decode. So yeah, I guess we'll see if that works out or not. So where I said write type section, here we go. This accepts now a array of func type, and again that's actually func type. Are you using PureT or formatting manually? I'm formatting manually. Not because I have anything against PureT, it's just that I haven't set it up and I can't be bothered because, well, maybe I could be bothered. I don't know. I don't care enough, I guess. So this is the types. So now, how is a type section actually encoded? So a type section is a section. We've done that with the thing outside here. And that's a vector of func types. Okay, so we write a vector, and this thing is actually a write func type B mapped over. Oh wait, that's not how that works. I've been writing in other languages too much. It's just map. So we're gonna map the write function. A write func type function over the types in here, and then this is going to complain because this needs to take a func type as an argument. Okay, and so now let's look at how func types are encoded, because this is the function we need to implement next. So a func type is our func types are encoded by the byte 0x60. And then the two result types in sequence, which are both just vectors. And I'm assuming that if we go and check what func type is defined at, it's actually a record. And so we could go ahead and say arguments and results and just pattern match that right away. And then we're going to write the arguments and we're going to write the results. And writing a result type actually accepts a result type, like so. And we're going to call that one tie over here. So how do you write a result type? Well, that's just a vector of value types. Okay, so we're going to do a write value type here, similar to what we did before. So this is a map, write value type. And we need to query in the buffer again over the tie. No, wait, what? Yeah, these are ties. This is not just one result type. Oh wait, the result type is an array, right? Yes, it is. So now we need to fix write, or we need to write. Oh, damn it. Value, can't type today. And this is a function from debuffer to value type to effect unit. So this is the buffer and this is the type, and I believe value type is actually a sum type. There we go, down there. So let's just do this for now. Not sure if that's going to work. We'll find out. There's a val type. There we go. We need to prefix all of these with an S. Okay, so how do we write value types? So I32 is 0x74. This one is 0x70. This one is 0x7d, and I think I've capitalized these just about everywhere else, so I'm just going to keep doing that. And this is 0x7c. And what we're going to do is we're going to add int 8 to the buffer. One of these. And I'm actually going to call this a tie because this is a result type, even though it's a list of value types. All right. That should be the type section for all I care. Right? Because we went ahead and we did write func type, which writes this thing, and it writes the two result types, which I think we did correctly as well. Okay, seems good to me. I'm gonna keep going then. So let's go back. Next up is the import section, and I don't think we've written that at all yet. Yes, we haven't, so let's do that. Section, write import section. Imports, I believe. And it's going to complain that that doesn't exist yet, which is correct. So where are we going to put that one? I'd almost like to do, well, I don't know. I'm just going to put him at, in here, and then I'll reformat the whole thing and think of a good structure after I've done that. Why can't I type today? So I want to write the import section, which is going to receive, well, a debuffer first, and then an array of what I believe to be imports, so s.import probably, and it's going to, again, return effect unit. So this is the buffer, and these are the imports. Okay. Hey, Gil, how's it going? Christian, I'm assuming, not Gil. Hope you're doing well. We're in the process of taking our abstract syntax and turning it into the binary Wasm format. Hello, Alex. Hope you're doing well as well. One of my regulars. All right, import section. This is the binary format? Yeah, this is the binary format. Okay, so an import section is a section that gets the number 2, So we start by write section, which gets the number 2, right? So now let's write the actual thing. Oh no. Work. That's the worst. Oh no. Well, yeah, the weekend's over, I can tell. But when I look at this, okay, so we've got a section with the index 2, and then the contents of that is a vector of imports. So I'm gonna map write import here, which we haven't defined yet, but we can do that in a second. And maybe actually, now that I think about this, I'm probably getting rid of all these write prefixes because they're not helping. So we're mapping that over the imports, and the whole thing is supposed to be a vector. So I'm just going to say write vec, like so. And then I don't actually need to do, I can just parenthesize this. Okay, so what does it want now? Write import, which is going to accept the debuffer and an import, and it's going to return effect units. So buffer and import. Now let's look at what an import is. So an import is a few things. So there's a module, and because we can't bind that name, we're going to need to, let's actually not bother with calling it something then. We also can't give the name import because that's also a keyword. Okay, so what do? We write out the name. So do we have write name yet? We don't. I'll need to look into that. So write name. No, we write the module first. So write name b of imp module, and write name followed by write name b imp dot name. And then we're going to finally write the import description. So import desk, like so. And let me put an extra underscore in here. So write name. It's going to be a little more interesting. So write name takes a buffer, and it takes a string, which is a name. I'm going to check if that we did give that an alias. That's useful. And we're going to return an effect unit from here. So write name is equal to, and this is the name now. So now how do we actually import this? So what is a name? A name is a vector of bytes which contains the Unicode encoding onto the name's character sequence. Okay, so what we need is to figure out if we can encode into a uint8 in JavaScript from a string. So what is this doing? UTF-8 and encoding and decoding. This is doing more nonsense. Can't I just... Okay, no, I'm gonna figure out. Can I just use buffers maybe? Buffers and typed arrays. Buffer instances are also JavaScript uint and typed array instances. All typed array methods are available on buffers. There are, however, several incompatibilities. Creates a copy buffer slash creates a view of the existing without copy separate. There are two ways to create new typed array instance from buffer. We'll copy the buffer's contents, interpret it as an array of integers, not as a byte sequence of the target type. Passing the buffer's underlying array buffer will create a typed array that shares its memory with the buffer. Okay, that's what I want to do. It is possible to create a new buffer that shares using typed array buffers. Okay, so how does that work? We declare. Okay, so I want to go this way. I say I want to make a buffer from something with an encoding, and then I make a uint array from that. Really? Okay, so the function I want here is, so here I'm doing add int 8. Now this is add buffer. Now let's write the function we want and then figure out how to get the implementation right. So I want to add a UTF-8 string. So I'm going to accept a string, and this is going to return the effect unit. And this is not going to be a buffer, this is going to be a string. So how are we going to do that? So we can make buffers from. Now my question is, can we also make UTF-8 just a uint 8 from string in JavaScript? Text encoding living standard. So is this a thing now? Can we just do this? Text encoder. Okay, does Node do this? I don't know. Let's figure it out. So if I were to say Node and then text encoder, that's a class. Let's make one. This is okay, so I can make a text encoder, and apparently it has the default encoding of UTF-8. Okay, so now what does this have? Encode. Can I give this hello? And this returns me a uint array, which supposedly is the U. Okay, I'm gonna assume that that works. I'm just going to assume that that works, though I don't know if it actually does, but that's good enough for me. Okay, so what do? We say bytes is are we doing too much copying if we do this? I think we might need to copy some of this to make that nice and quick. But maybe we can actually do this instead and see if that works. Okay, so I'm going to pretend that there's a function we can write which gives us a debuffer from a string. And I'm going to pretend like that function just calls bytes. And then encode UTF-8 with S. I'm going to run. No, I'm just going to implement this naively, And then I'm going to return something here, but just think about that for a second. What do we implement? What kind of functions here? Set, allocate, subarray, and when. I do need to figure out the size of this. I'm assuming I can just ask for its length, but I'm not quite sure. Can I call this? Oh, I can just say dot length. Okay, so dot length works. So, okay. Really, if we can get just get the length of this thing, we should be fine. We're just going to put the position and the length to the same value afterwards. Yeah, okay, so let's just do that. Set impl. I'm going to say length impl. It's going to be an effect one, which is going to have this type, and we're also going to implement. And I'm not going to specify that up there. I'm going to specify that one down here. Encode UTF-8. And I'm actually also going to make that an effective N1, which is going to take a string and return a uint8 array. And we're going to run effect fn1 here. Okay. And step one is going to be to implement these two functions, I believe. Fails to parse because this is also not implemented. Okay, so let's implement these two functions. So the first one is length. So dynamic buffer.js. And in here we're going to export length impl. It's going to accept an array. It's just going to return array.length, like so. And then we're also going to implement, and that should probably be somewhere down here, encode UTF-8. And that's going to accept a string and return the array. And the way it's going to do that is it's going to say that the text encoder is a new text encoder. And that, I'm assuming, is going to initialize that to have UTF-8 encoding again. And then we're going to encode the string and return the result of that. And hopefully, what we can do here now then is to say, get the len of the thing. So we say, and we can actually probably call that thing size. So I'm going to say run effect fn1 length impl on the bytes. And then we're going to return a debuffer. And well, we're going to actually need to be a little more tricky than that. So what we want bytes, we want size, and we don't want position. Okay, but all of these are refs. So what do we need to do? Well, we need to say this is B's, and this is size. Or I'm actually gonna give them prime here. So bytes prime, size prime. And then we're going to say bytes is a new ref. With the contents of bytes prime. And size is a new ref with size as its initialized starting value, and position is the same here. That's actually also going to be size here because the buffer starts out completely filled. And so what is it not liking about this one? Size of ref int. Did I call it length? I did call it length. Okay, so let's call it length then. That makes all of this a little more consistent, which is nice. Okay, here we go, and this is length. Like so. All right, cool. And so now it's asking us to do, so now add UTF-8 is just add buffer B, and then we're going to from UTF-8 the string. And just because I'm not sure if it recognizes that, I'm gonna say newbie I'm gonna call it encoded or something. Okay. And that should do it, hopefully. Does this compile? Compiles. If it works, that's a different question. I'm gonna check out the definition for text encoder on MDN if I can. Okay. And so encoding always returns UTF-8. Takes a destination U into 8 array tuples resulting into it returns. Okay, so we can also write directly into a uint array. We could use, but we don't know how long the encoded value is going to be, so we're not going to do that. I'm assuming this thing keeps on resizing. I don't know. I'm not going to bother with that. I'm assuming that is good enough for us. All right. So let's hope that works. So now we have an, we do need to add the add UTF-8 to our exports. And now we should be able to say inside our decode module, so encode module, should be able to say where we said write name, that this is just write just debuffer dot add UTF-8, and we don't need these parameters here. Okay, so now write name is defined. So let's do write import description. And this is going to accept a debuffer and an import desk, and it's going to give us back effect note. And so what does an import desk look like? Oh, that's actually one of those. All right, so let's see how those are encoded. It's an import description. Again, starts with, okay, so it starts off by writing a certain byte and then these things. Okay, so let's do that. So it's either an import func with an index, and let's keep going. Import func, import table, import memory, and import global. And all of these are holds for now. All right. So import func. What is import func? That carries around with it a type index, which I'm 100% sure is just an AU32. So let's see. So what are we going to do? If it's an import func, we're going to first add an int 8, which is going to be 0x0, so just 0 in it. And then we're going to add the type index, which I'm assuming is encoded as a U32. So yeah, we're going to use unsigned LAB128 for the index. Okay, so next up is a table type, which is defined over here. Okay, so how is a table type defined? Well, step one, we need to encode, we need to write by 1 byte. So let's start with that. let's write 1, and then we need to write the table type. And a table type, if we go and check here, is a thing. So we're going to actually write ourselves a helper for that. So this is the table type. Okay, so let's do that. How does one write a table type? Well, down here it says that a table type has limits and an element type. Okay. So, how is the table type written? It says here, we start by writing out the element type and then we write limits. And an element type, we're just going to write 0x70 because that's the that's the only element type we can write so far, if I can if I read that correctly, but I'm still going to write a function for this because eventually there might be more. So write element type is going to be a function that takes a debuffer and an element type and produce like so, and produce an effect limit. Oh, I can't type today. Write element type, and it's going to, well, case really, and then for now, because there's only one, we're going to get func references in here, and those are added by adding an int 8 to the buffer, which is going to be 0x70. Okay. Seems good to me. So we're going to write the element type, and then we're going to write the limit. Limits. And how does one write limits? Okay, here it says. And then there's two ways of writing limits. So that's because one of the properties of these limits is optional. So we're going to accept a debuffer and the limits. And what are the limits? There's two ways of writing those. So limits is always a record of mins. And I'm going to say, we're going to say min and max here. We're going to say case max of nothing. That's the first case. If min is, if max is nothing, we're going to write an debuffer add int 8 of 0. And then we're going to write the minimum, which is an unsigned LEB 128 of the minimum. And if we actually have a maximum, then we're going to write that maximum as well, but then we have to also change this into a 1. It's going to complain about the missing import, and this needs to be max prime, like so. Exactly, and we write n first and then m because that's min is m. Yeah, like so. That looks good to me. So now, if we backtrack, that means we're writing table types correctly. So now we should be able to say we want to import a memory. So how does one encode the memory type? That's just the limits. Okay, so let's start here. So if we're encoding a memory type, we write the byte. We write 2 first. So do this thing, but write 2 instead. and then we're going to write the memory type. But if we check what a memory type is, that's just limits. So what we're going to do is we're just going to say, okay, well then write the limits into, let's go, like so. And then how do you import a global? Well, you start out by writing the magic byte 3. And then you write a global type. And a global type is, okay, it's a bit more interesting, so let's write that. So we're saying write global type. I have like 10 more minutes. Let's see if we can get through these import descriptions by then. So we're going to write a global type, and that's really what this is. Like so. So how does one write a global type? Well, let's write the type first. Global type to effect unit. This is a buffer, and this is the global type. Now, how is a global type defined? It's defined down here. So it has a mutability and a type. And because we can't call it type, I'm just going to call it tie here. Maybe in that case, I'm actually going to call it global. I'm going to pattern match these like so. Okay, so how is a global type encoded? Well, we start by encoding its value type and then its mutability. Okay, so encoding a value type, I don't know if we have that yet. It looks like we do, so that's good. So we're just encoding the value type, and then we're encoding the LM type. No, then we're encoding the mutability. So write mutability, and really, let's actually say, yes, let's do that. So let's write mutability. And that takes mutability as its argument. So copy this. This says mutability. So does this. Like so. And this is just b equals case underscore off. And here we can actually say debuffer dot add int 8, and then we say case of, where do you find mut and var or something? Var and const. So var is a mutability for sure, and var is 0x01. You can probably not even see that, right? That's terrible. It's down here. No, you can. Okay, so you can. Okay, cool. And then the other one is const, which is 0. So const is 0. Like so. What does it not like? Yeah, this is the mutability. So this is mut, and I'm going to call this the mut, like so. And then this needs to be a do. And I think that should be our imports, because now that this module is compiling again, we have covered all of the different import types. Wait, yeah, those are here, exactly. Cool, so, okay, we've got 8 more minutes. I'm gonna go ahead and see if we can't write the function section, because that shouldn't be that hard. That's just a mapping. Exactly. Okay, so the function section is easy, so let's just do that one real quickly. So let's write the function section. And that's actually a function we already have. So let's look for it, because we needed to write that before. And rather than just encoding a, well, not encoding anything really, now that this has to accept an array of funcs, like so. So these are the funcs. We're still writing the section 3. We're writing a vector, but now we need to, well, look at what func is really, and that's that. Wait a second. The function section has the ID 3. It decodes into a vector of type indices that represent the type fields of the functions and the funcs component of a module. The locals and body fields of the respective function are encoded separately in the code section. Okay, so it actually is a bit more tricky because this does not encode. So this is the func sec. So the locals and body fields are encoded separately. So do we accept the full func here and then map out the indices? I think we do. Okay, so what do we do? Well, a func, as you can see down here, has actually a couple of fields. What we're going to do is we're going to say, well, we're going to write a vector. And that vector is actually going to write func type. Wait, what is this thing again? Do we not have a function for this? Type index, that's just a U32, right? So let's just say a U32. So that's an unsigned. Did I say? I think I wrote U32. Yes. Let's just make sure we define that correctly. So what write U32 is defined as unsigned LDB. That works for me. And we need to first extract the type, like so, from all of these funcs. And this needs to accept the buffer as its first argument, like so. All right, I think that's the function section. And this needs to accept the funcs, I think. Yes, that's the right. Okay. So funcs. If we were to keep going, what's the next one? We've got 5 more minutes, so maybe this one is easy as well. The table section. That looks simple enough to me. Let's try that one. So we're writing the function section, so now let's write the table section. Like so. So tables, yes, let's add that one here. So write table section, and again we're going to accept the debuffer, and then an array of table, and this is going to return effect unit, like so. So what are the tables? Well, let's start out by saying that we're writing section 4 here, I believe. Yes, 4. So we're going to write a vector. And what is the vector? Well, we're going to map a function over the tables, that's for sure, and that's probably going to be write table B. Right, okay. And a table is encoded by encoding its table type. Wait, haven't we done this before? I feel like we did this. Or did we do that from memories? No, didn't we do table type? Yeah, write table type. When did we do that? Where is this used? This is used when we're writing the import. Oh, because you can import a table. Yeah, that's handy because we can just say write. Yeah, that's cool. So let's do that. So write table takes a debuffer and a table. Okay, and so how is this implemented? Well, this is actually just write table type. Are these the same? Well, according to the spec there, but if I go in here, oh, I need to say type first. Okay. Okay, that's a little annoying, but that's fine. So this is the table, and we're getting its type, like so. All right, that works for me. And that should be the table section. Yeah, and now I'm out of time here, but I'm going to leave it to do continue below. So, I mean, that's pretty good, right? We implemented the encoding of 4 sections in one session. Unfortunately, somewhere down here, when we encode code, we'll have to encode all of the instructions, which is going to be a bit more work. But for now, I think that's good enough. I'm just going to leave it here. Thanks everyone for watching, and I'll keep trying to stream every day, so probably see you tomorrow. Bye bye.